Okay, so good morning again to everybody. Good day. So next speaker is Professor Gregory Panasenko, which is internationally known, so he need not really to be introduced, but anyhow, I say a few words for young people also. He is a distinguished professor of the University Jean Monnet in Saint-Étienne, France. He's also I don't know, it seems he's also in the Institute of Applied Mathematics in Vilnius. He's several research institutions. He got a medal from the USSR Academy of Sciences in '86. He works in homogenization and partial differential equation, mathematical modeling of heterogeneous media. He wrote 2 monographs, about 150 articles, proceedings, and he directed more than 20 PhD students. Okay, he has several grants. He coordinates numerous international projects and organized a lot of scientific events. I think it's enough to introduce you. So you can go on with your talk on multi-continuum model for the wave equation. Please.
Okay, thank you very much for kind words, and I'm very glad to be invited to this conference. Um, I don't know, there are several students, I think.
Yes, half student, half faculty, actually.
Yes, so I would like to make this presentation in some more comprehensible way for the students, but the topic with all the proofs and with all the details is a little bit technical, so I will skip some parts, but I will leave the whole presentation to the organizers, and it will be in free access. So I will talk today about the multi-continuum model for the wave equation in a high contrast laminated beam. This talk corresponds to the publication, the paper that appeared in 2018 in the Journal of Mathematical Science. So this journal, to my mind, is a very good journal with a very honorable editorial board, and it publishes a lot of papers of Russian scientists, and although it is not the so-called Q1 journal today, but its editor-in-chief Tamara Rashkovskaya makes her best in order to lead this journal to the best places. The topic of my talk will be concerned to the homogenization procedure, but this homogenization procedure will be presented not in the same way as the students heard in the previous lectures by very well-known distinguished lecturers, because mainly it was presented as some convergence theorems based on some functional analysis tools. I will present it in the form of as a result of some expansions, asymptotic expansions. And I will show how these asymptotic expansions are justified. And it also uses functional analysis, but maybe in a little bit less portion than the convergence versions. Although for this we have to pay by some regularity of the right-hand side of the equations, which should be homogenized. The second difference is that normally, classically, the homogenization theory says that we can replace the heterogeneous medium by some homogeneous medium, where everything is close to some function which doesn't depend on small parameter. And there are some examples that are well known now when it is not so, and when we need more detailed analysis of the leading terms of the asymptotic approximations. And so here it will be also the case, because the limit model will not be, sometimes it will be completely homogeneous, sometimes not. And when it will not be completely homogeneous, we will get the so-called multi-continuum model. What is multi-continuum? Multi-continuum is the model that describes the coexistence of several continuum media at the same point. And so we will provide the analysis of this problem. So what is the domain? The domain will be the beam, and the cross section. This beam is will be long. Even we will not consider it with some boundary conditions at the cross sections. It will be periodically continued, but the period with respect to the longitudinal variable, it will be of order of 1, while the cross section will be small parameter. The diameter of cross section will be small with respect to this longitudinal characteristic size. So in this problem, there is very standard for thin domains parameter that that is called normally epsilon, and it is the ratio of the thickness of thin structure to its length. In the problem, there is another parameter that is the high contrast, and it is high. It's big parameter, much greater than 1. It is the stiffness of the material and its density. And we will we will consider such a beam which is laminated, which consists of layers, alternating layers, which are colored here by red and yellow colors. And red color corresponds to a stiff and heavy material, while yellow color corresponds to a weak and light material. So there are two parameters, small epsilon, d divided by L, and omega, which is the parameter characterizing the ratio of stiffness and density of the layers. As this model, the limit model will correspond to the multi-continuum model, and multi-continuum model often is non-local in space. So I cite some high contrast homogenization papers with the appearance of non-local in space effects that were obtained in the papers by Kruslov, Panasenko, Kruslov, and several of my papers in 80s, and by Orio, where in these papers the standard procedure of homogenization, it was noticed that it doesn't work, and the limit problems have this multi-continuum structure. Also, we can say that one of multi-continuum models was also corresponding to the double porosity model, which was introduced by mechanicians first, by Barenblatt, Желтов, and Kochina, and then it was derived via the homogenization theorem. So this was the first paper on the passage from micro to macro by Arbogast, Douglas, and Hornung. And in the present lecture, we derive also multi-continuum wave propagation model in laminated beam with contrasting stiffness and density of the layers using the technique of multi-component homogenization. This technique is based on special ansatses for the asymptotic expansions, especially prepared for the high contrast materials. So to introduce rigorously the structure of the domain, we will denote by, first we will consider this beam as dilated 1 over epsilon times. Then we will see the beta is the cross section, the whole cross section. Then alphas will correspond to the parts of the cross section occupied by the strong material, the heavy and rigid, and yellow parts by light and soft material. And these yellow parts will be denoted sigma. So alpha is strong, red, and sigma is soft. So here it is given the rigorous definition of all these subdomains. And so we introduce the coefficients of the wave equation, and the main object will be the wave equation. The coefficient that characterizes the stiffness of the material, it is equal to omega multiplied by some constant kr of order 1 in all domains alpha r, which are red domains, stiff and heavy domains, and it is equal to k, just a constant of order of 1 everywhere in yellow parts, sigma r. and the density rho of the cross section in the dilated variables has the same structure, omega rho r in the red zones and rho constant, which is equal about 1 in yellow zones. Then we consider the contraction 1 over epsilon times of this bar, and we get b epsilon as the cross section, the whole cross section, alpha r epsilon, they are stiff zones, and sigma r epsilon, there are soft zones. The whole domain is denoted G epsilon. It is the Cartesian product of R by beta epsilon, and one period is cut of this G epsilon. It is denoted G epsilon 1. And so we consider the wave equation that is written here with the right hand side f that is rho omega and k omega are defined just before. You remember they have very high values at the red layers and very of order 1 in yellow zones. The right hand side f it is proportional to omega to scale somehow. It's a linear problem, so we may scale it as we want, and this is just the scaling parameter omega, and f is one periodic function of x1 which is infinitely smooth. In fact, we do not need to have infinite derivatives, but the number of derivatives which we have to have from f is as high as many terms of asymptotic expansion we want to justify. So its regularity depends on how exact solution we want to obtain. And the boundary of the rod of this beam, we set the Neumann boundary condition, so it is free boundary, and the initial conditions are given values of the unknown function and its derivative. And we assume that the right-hand side, f, is equal to 0 for several first moments in time. So this was the classical setting of the problem, and you should know that for the linear problems, the main linear problems of mathematical physics, there are special theorems that are proved that for smooth boundaries, smooth interfaces, this setting is equivalent to the weak formulation. But if we write the classical formulation, that instead of the equation at the interface of different materials, we need to add these interface conditions. So this problem, classical problem, is equivalent to the corresponding weak formulation, And knowing that the right-hand side is very smooth, this formulation can be given in the space H2, 0t, H1, periodic and X1 functions. So this formulation is given here. The proof of the existence and uniqueness of the solution is well known, and it is given, it is based on the Galerkin method. And we can get the following a priori estimate, that if we introduce such a norm that is written here, then we have these a priori estimates. The solution is bounded by the constants, which are independent of epsilon and omega of small parameters, and the right-hand side are in these norms. It can be proved very easily. So now I would like to describe the main results first. And to this end, I will use the following definition of L convergence. So I will say that two functions, one L converges to another if their difference in the norm L2 of G1 epsilon 0 t being normalized by the square root of G epsilon 1, it is in fact the measure of the beam, tends to 0. So in fact we have to normalize by this value, because L2 norm automatically includes this factor if the difference is of order of 1. In fact, in all the results, we can not only prove that it tends to 0, but we can prove to, we can evaluate the difference in this norm in function of epsilon and omega. Okay, so the result depends on the value that is epsilon square multiplied by omega. Epsilon is the ratio of the thickness to the length, and omega is the contrast between the layers. And if this parameter is small, then we get the limit model that is a standard model of the homogenization of a beam. And it looks like the following model, that if epsilon goes to 0, omega goes to infinity, epsilon square omega goes to 0, then the solution is close to the solution of such one-dimensional in space problem, where V0 is the solution of the wave equation, one periodic and X1, and with the initial conditions that are 0. The coefficients here are constant, and they can be calculated explicitly. Completely another is situation when it is dramatically changed, when epsilon square omega goes to infinity, or when it is a constant. In this case, we obtain the so-called multi-continuum homogenization. And namely, the leading term of an asymptotic expansion depends on the microscopic variable and has such a form. So here you see the functions VR, depending on x1 and t, and the number of these functions Vr, that is L over 2 plus 1, it corresponds to the number of stiff and heavy layers. The coefficients Nr depend only on fast variable, and they will be described below. The second term is epsilon square omega, so it may be very big, multiplied by the right-hand side, f, and multiplied by another function that is called m0. Now let us describe nr, m0, and then what are vr. So the picture for nr is as follows. It is such a cake-shaped function, which is equal to 1 at one red layer, stiff layer, and then it descends to 0 in two neighboring yellow rings, here and here, from 1 to 0 as the solution of the Laplace equation. And then it is continued by 0 everywhere. Out of these three rings, it is 0 everywhere. The m0 function, it is the solution of this equation, Poisson equation with the right-hand side, which is equal to 1. And with Dirichlet condition at every yellow ring. So its profile looks like this. And so we have described the coefficients nr and m0. m0 is multiplied by the right-hand side, and nr is multiplied by vr, and vr are the solutions of either independent, completely independent one-dimensional wave equations. So we have as many wave equations, how many layers, stiff layers we have. It is in this case, or these equations start to be weakly coupled by these terms with the coefficients dr, which are defined with help of this cake type function nr. So in all these cases, we can prove the convergence in this sense that these issues are going to 0, and even we can evaluate them as powers of epsilon, and we can construct the complete and justify complete asymptotic expansion for all these three cases using the technique from one of my papers that was appeared in there is this reference 1990. I would like to say that also this problem here can be, if you express one of VR via another VR, it becomes non-local. And I would like to cite also the paper by Murat and Seeley, where they have obtained in 2000 also some non-local effects for the elasticity equation when it is anisotrope heterogeneous elasticity, where also they obtained for beams the non-local effects. So what is the practical consequence of the fact that this beam may be multi-continuum? It means that we can have as many wave velocities as many stiff and heavy layers we have in this model. And they propagate either completely independently one from other, or if epsilon square omega is a constant, they may weakly interact. Now, several words about the construction of asymptotic expansion. So, as I've told, I used the asymptotic expansions approach. In this approach, you need always a conjecture that shows you what is the form ansatz of the asymptotic approximation which you have to seek. If this conjecture is done, then the procedure is relatively not too complicated. You have to plug this ansatz to the equation, and you get several auxiliary problems independent of epsilon. First, that you have to solve, and you get that after this plugging, you obtain the right-hand side with small remainder. And you need to evaluate this remainder. And then, if you want to get the evaluation of the difference between the exact solution and the approximation, you apply the a priori estimate that we have cited in the very beginning. And using this a priori estimate, you get as high approximation as you want, but paying, of course, by the regularity of the right-hand side. In particular, in the case when epsilon square omega is small parameter, we get this estimate for the difference of the exact solution and its approximation. In the case when epsilon square omega tends to infinity or is equal to constant, we have a little bit more complicated ansatzes, which are related to multiple homogenized functions V. And this approach as well gives us all auxiliary problems. And finally, we can calculate the remainder. And evaluating this remainder, applying again the a priori estimates, we obtain these error estimates. So, concluding, I would like to just present the main idea of justification of the asymptotic expansions. If we need to solve some problem which depends on small parameter, we prove, of course, as always in mathematics, the existence and uniqueness of the solution and its and an a priori estimate. And in this a priori estimate, even we can have the constant that may be badly dependent on small parameter with negative power of epsilon. It's not too dangerous if it is not exponential. It is not too dangerous for the asymptotic expansions method, because we always can improve the order of approximation, adding new terms and paying by the regularity. Then, so we have this equation, we have this a priori estimate, and then we construct some asymptotic expansion, truncated asymptotic expansion, that being plugged to the equation gives us the right-hand side with some remainder of order epsilon power k in some norm. And then subtracting, I consider only linear case now. In non-linear case, this technique to justify it is less easy to do. Subtracting this equation from what we have obtained for the difference, we get this equation, and applying the a priori estimate, we obtain the error estimate that we want. So in fact, the main part of so-called formal asymptotic solutions may be justified in this way. So we construct some function that gives us small residual, but if we have the a priori estimate, we can easily prove that the difference between the exact and asymptotic solution is small. And so for linear problems, there is no any obstacle. For nonlinear problems, sometimes this scheme also works. Sometimes we need more complicated analysis. Sometimes we don't have uniqueness of the solution. So then it is more complicated. Okay, so thank you for the attention, and maybe you have any questions.
Thank you very much for this talk and for being on time. There is a question from Adrian Muntean who asks if you can share the slides of the presentation. I think this is the case.
Yes, of course. I will leave to the organizers.
Okay.
I can send it as PDF file. Yes?
Perfect.
Yeah.
Okay, thank you.
Yes, we will upload all the talks if the author agrees to it. All the talks and the slides will be there in the ICTS website.
On the other hand, if there are other questions, you can write or talk.
Excuse me, epsilon square is a critical sites.
Yes.
For other sites, you have a result.
So, in fact, if epsilon square omega goes to 0, then we have only one equation, so that the beam is not multi-continuum, it is monocontinuum, and we have standard one-dimensional wave equation. And if epsilon square omega goes to infinity, we obtain in the limit the situation when we have as many beams coexisting at every point, how many stiff and heavy layers we have. And in the critical case, they are no more independent, and they are weakly related by these terms. And in this case, this multi-continuum model may be considered as non-local in space model. because these beams, they coexist and they feel one other, but they are relatively independent.
Thanks.
You're welcome.
Okay. Well, if there are no other questions, I propose just 3 minutes break